Okay, so the polynomial we were just looking at on that video, they're all part of a group called Taylor polynomials, which is named for a mathematician of old, a man named Brooke Taylor. He's an English mathematician. These are named after him. And so here is kind of the basic construct, and this might make a lot of sense based on what you guys saw that first day. The basic construct for a Taylor polynomial would be, the first term is always going to be f of c, and c is going to be our centering x value. So in that one that we looked at a second ago, the centering value was 0. That would mean that for this, if we were going to make this, then c would be 0 in every instance. Okay. If we were talking about the second one we looked at, where it was centered at 1, then in every instance c would be 1. Make sense? So c is the centering value. The first term is going to be simply f of c. So that basically means that the y value of the transcendental and the y value of the polynomial will exactly match. And I think maybe you saw that on those graphs, right? Like when we first looked at those lines, the y value is exactly matched up. Well, then if we want these curves to start conforming to each other, then we need the slope at the centering point to be the same as well. And so do you see how the second term would be f prime of c, f prime being the slope, right? So we're saying basically we want the slope of the curve and the slope of the polynomial to be the same at the centering point. Well, then we're like, well, what if we wanted the concavity to match? Then wouldn't we need the second derivatives to match? So we'd find the second derivative of the curve, and we'd make sure the curve's concavity matches the polynomial's concavity. That would give us our second term. And then we want the third and the fourth and the fifth and the sixth and the seventh derivatives to match. And so that's, of course, what this dot is. We'd go all the way out to the degree n, whatever degree we're asked to do. And we'd stop it there, right? We'd say after, the seventh degree we stop, or after the third or the fifth or whatever it is degree, we stop, and that would be our polynomial approximation. You saw with the e, I didn't quite fill up the whole screen, right? I didn't get the whole screen to converge, and so I just stopped because, frankly, I ran out of time, and some students came in and needed some help, so I just quit. But with the cosine, you saw that I just about filled the whole screen with it. If you wanted to fill the whole screen, if you were looking at it from a graph perspective, just add more terms. Right? Just keep adding more and more terms, and your interval of convergence will change. Okay? Question, McKenna.
How do you find C?
You don't find C. It's told to you. They'll say find the fifth degree Taylor polynomial centered at x equals 2. Therefore, we'll use a 2. Yeah. Okay. A note over here to the side. I think maybe I've mentioned this before, but in case I haven't, that f with a parentheses n up there means the nth derivative. So please don't think that, like that notation of f with the 5, don't think that that's f to the fifth, right? It means the fifth derivative of f. It's the parentheses there that kind of help us with that. Of course, the reasoning is if we're going to do like a 12th derivative, you don't want to go like 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I lost count. Got to start over. You're like, we just put parentheses 12. We know it means the 12th derivative. Make sense? And you might think, hey, that's ridiculous. How hard would that be? Well, if your transcendental is e, what's the 12th derivative? E to the x, right? Yeah, so if you start off with e to the x, your 50,000th derivative will be e to the x. So it might not be as complicated as you think. Same sort of idea with sine and cosine, right? It's just going to flip back and forth. You could figure it out. Not that we're going to do a 50,000th derivative, right? No, we're not going to do that. Just too much time. So I would say that all of these polynomial approximations that we're going to be looking at, they're all Taylor polynomials, but there is a different term that you'll often see, and that is a Maclaurin polynomial. And if you take a quick look here and you try to compare the Taylor polynomial construction with a Maclaurin polynomial construction, how would you say Taylor and Maclaurin are different? C is always 0, right? So if you notice, they are exactly the same. They really are, other than c is 0. Okay, so the x minus c's all become x minus zeros, hence they're just x's, and all of the f of c's and f prime of c's and f double prime of c's are just f of 0, f prime of 0, f double prime of 0. So you could say that a Maclaurin polynomial is simply a Taylor polynomial centered at 0. Make sense? We would, just for sake of terminology, we would never say that there's a Maclaurin polynomial centered at 5. Maclaurin polynomial, by definition, is centered at 0. Okay, Maclaurin is a Scottish guy. I guess they have good mathematicians too. Whatever. Let's see here. So there might be two ways you could see this done. You might see a question that says, write the 7th degree Taylor polynomial centered at 0. They could have just said, write the 7th degree Maclaurin polynomial, right? It's the same thing. Or it could say, write the Maclaurin polynomial 4th degree. They don't have to tell you where it's centered. That makes sense? So if they tell you it's Maclaurin, they don't really have to tell you where it's centered. McKenna, that kind of goes along with your question a little bit. Maclaurin means centered at 0. Taylor, they kind of have to tell you where to center it. And when I say they, I mean me. So, yeah. Okay. Any questions? So I thought we would do this first one here together just to kind of, I feel like maybe we've sort of kind of proved that this is all true and well and good and everything, but I thought we could maybe prove this to ourselves a little bit more concretely. This might seem like a silly thing to do, but it might serve a purpose. So let's see here. Number 1 says, find the 4th degree Maclaurin polynomial for 2x to the 4th minus 3x cubed plus 5x plus 7. It's a very odd question. I don't know that I would ever ask you this other than right here, because what am I asking you to use in a polynomial to approximate? I'm saying, yeah, approximate a polynomial with a polynomial. And so if you think about it, what should the answer be? I don't know. Let's find out. So, yeah, well, it better be a polynomial, right? Because it's a Maclaurin polynomial. Let's try it out.
Good job, Melissa.
She's right. She is definitely right. Let's try this out and see what happens. So I'm going to say my Maclaurin polynomial. I'm just going to say P sub 4. So that just stands for 4th degree polynomial equals. So your first term is going to be f of 0. Okay, so this is our function up here that we're trying to approximate. So I'll just put equals f of x there. So what is f of 0 if that's my polynomial? 7. Okay. Okay, now you're looking back up at that Maclaurin construction. What is the next term? The next term is going to be f prime of 0. So let's find f prime. F prime would be 8x cubed minus 9x squared plus 5. So what's f prime of 0? 5. Okay, so plus 5x. And again, you can kind of see that Maclaurin construction right above. The next term we need f double prime. So let's find f double prime. 24x squared minus 18x is equal to f double prime. So what's f double prime of 0? 0. Okay, so I'll write 0x squared over 2 factorial, just to keep the consistency right with the construction there. Okay, and then f triple prime is what's going to give me my 3rd degree term. So that would be 48x minus 18 is equal to f triple prime. So what would you guys say f triple prime of 0 would be? Okay, so that would be minus 18x cubed over 3 factorial. And then we need our 4th derivative, so I'll just write this. 4th derivative of f is 48. So that means the 4th derivative of 0 is 48. So I'm going to write plus 48x to the 4th over 4 factorial. So you see how I basically followed that Maclaurin construction, where the degrees and the factorials kind of move up together. We plug in a 0 at each point to find the value of the increasing derivatives. Okay. So this might not seem all that great, but let's simplify it a little bit and see what happens. P sub 4 equals 7 plus 5x. That 3rd term is 0, right? So I'm not going to bother writing that. What's 18 over 3 factorial? 18 over 6, right? Yeah, 3. So it'd be plus 3x cubed.
Wouldn't that be minus?
Or minus, sorry. Yep. Thank you. And then the last one is plus. 48 over 4 factorial. What's 48 over 4 factorial? 2, right? Because it's 48 over 24. So plus 2x to the 4th. Now, when you look at our polynomial approximation for our polynomial, look, they exactly match. Doesn't that make sense?
That's exciting.
Shouldn't they make sense? Shouldn't they be perfectly aligned? Because it's a polynomial approximating a polynomial. Now, when we start trying to use polynomials to approximate transcendentals, that's where things don't line up at all, other than at the centering point. But then we can control our error and say, oh, the error is too big, let's just add a couple more terms, and we're good. Make sense? Okay. So I guess at this point, my takeaway would be, do you trust at least a tiny bit that this sort of works? Okay. I hope you do. Okay, so let's take a look here then at number 2. Number 2 says, find the 6th degree Maclaurin polynomial for f of x equals cosine of x. And once we get that, we're going to use that 6th degree polynomial to approximate cosine of 0.1. Okay? So I thought maybe I'd start off with a term or two and kind of get some momentum and see if you guys can finish this off. So I'm going to I'll write this kind of right here in the middle, because I'm going to have to do a little bit of work to make this work. So I'm going to say p sub 6 of x equals. So it does say Maclaurin. So Maclaurin means centered at x equals 0. Or you could say c equals 0 if you wanted. So the first term is always going to be f of 0 for Maclaurin. So what's f of 0? 1. Okay, so you saw this maybe on that first video. Do you notice like the tangent line was y equals 1? And this is cosine again here. So that's the 0th degree term. So to find the first degree term, I need to use the first derivative. So my f prime of x equals negative sine of x. Therefore, f prime of 0 equals what? 0, yeah, sine of 0 is 0. Okay, so then this is kind of like that one we just did where one of your coefficients, the f prime of 0, is just 0. So if you wanted to, it probably would be a good idea at this point to write 0 x to the first over 1 factorial, technically, if you want to kind of see how the pattern builds. I'll do one more here with you. So I'm going to say f double prime of x would equal negative cosine of x. Therefore, f double prime of 0 would be negative 1. So this would be minus 1 x squared over 2 factorial. Again, I'm just trying to use that Maclaurin construction that you guys have above on your papers. I'm just kind of trying to transfer that into this one. So if you would, we're obviously up to the 2nd degree. This says find the 6th degree. If you would, see if you can take it up to that 6th degree. Again, just kind of practicing using that Maclaurin construction to build this out. I'll give you a few minutes to try this. And hopefully you'll see a pattern. Definitely an alternating series. He's right. That's important. Anything else jump out to you? Yeah, exponents are only even. And that's because whenever you look at your odd derivatives, what do you get? 0. Whenever you do your even derivatives, you get either 1 or negative 1. That helps create the alternating pattern, and it eliminates all of the odd terms from the mix. Keep going so you can finish it out. So if we clean it up, are you guys getting this pattern here? It'd be p sub 6 of x. First term is 1. Second term, we obviously already did this. Do you guys get a next term of plus x to the 4th over 4 factorial? Mm-hmm. And then, once again, that 5th degree derivative turned to 0. And so then your last term for this polynomial, at least, would be this. You guys see that same pattern? So you can see that the Maclaurin series for cosine is alternating, and all of the degrees are even. And hence, it kind of agrees with the idea that cosine is an even function. Let's see here. Are you guys getting busy graphing this? Are you seeing? So this doesn't really, like just the 6th degree doesn't really cover the standard window all that well. You got to go pretty far out there into the 20s to get that to happen. So can you see how this, around 0, is a pretty decent approximation? Maybe you can see that on your graph. It's not bad. But if you moved out to like x values, say like 5, 6, 8, or 10 or something, the approximation would get pretty bad pretty quick, right? It's going to be off by a lot. So this says use that polynomial to approximate the value of cosine of 0.1. So let's do that. Let's take a minute. Use your calculators, and if you just inputted this into your graph, it's pretty easy to evaluate it. So I would say let's find p sub 6 of 0.1. It's going to be some crazy decimal. Once you think you've got it, why don't you let us know, and we'll do some comparing and kind of see what we've got. Try to connect it back with what we did with alternating series. Anybody got it? 0.995. Let's go with a few more decimals. 0.04. 1653. We all agree on that?
Yes.
Okay. So then, just for sake of comparison, let's also do cosine of 0.1. I don't know what this is either, so let's see what. How close is it? Is it exactly the same out to the 3?
Yeah.
Nice. Okay, interesting. So 0.99500,416. Do we all agree that that's it?
0.999.
Say it again.
I got 0.999999847.
Oh.
Yeah, I got 0.99500,41653.
You guys in degree or radian?
Oh, I might be in degree. This is,
Is that it?
Yeah.
Okay.
Thank you.
It was close enough where it seemed like it was
Yeah.
feasible, right?
Yeah.
Interesting. Okay, so I'll tell you what, this is actually going to be a moment when we can be better than our calculator. Because right now, isn't the calculator telling you that the polynomial and cosine are exactly the same at 0.1? Let's show the calculator a little something here. How about this? It's an alternating series. No, we can. We can definitely show the calculator wrong. This is an alternating series, right? And so for an alternating series, the maximum error is less than or equal to the first neglected term. So I'll put this in a different color. But based on what you know about this pattern and what you saw with forming the Maclaurin polynomial, what would you guys guess would be the first neglected term off the polynomial? Like, if I kept going with this, what do you think would come next? X to the 8th over 8 factorial. Agreed. So I'm going to put that. So this would be my first neglected term, right? So then if I thought about this, when we found p sub 6 of 0.1, didn't we just plug a 0.1 in there? So what I can then do is I can say this. I'll attempt to use some very good notation. I'm going to say that the absolute value of p sub 6 of 0.1 minus cosine of 0.1. This would be my error, right? So basically we're saying polynomial approximation minus real value. That's our error. And that should be less than or equal to 0.1 to the 8th over 8 factorial. That would be the first neglected term in the series that we use to approximate cosine of 0.1. So maybe use your calculators. Let's figure out what that 0.1 to the 8th over 8 factorial is. Sure, I might give it to you in scientific notation. It's going to be pretty small. Isn't this cool? You can tell your calculator wrong. And here's by how far you might be off. Anybody got it?
2.48 times 10 to the negative 13.
2.48 times 10. That is a small number, right? 10 to the negative 13. So we're obviously really close to our centering value of 0 when we think about the 0.1 that we used. But just with a 6-degree polynomial, just those first 4 terms, the error is super tiny, so tiny that your calculator can't even detect it. In fact, rudimentary calculators, like way back when, used to actually use a process like this to approximate cosine of 1 or sine of 2. They use a different algorithm now. This is what they used to do. Anyways, can you see how a calculator could do this? If everything was polynomials, it's pretty quick and easy to calculate. Anyway, So is that a good connection for you guys back to the alternating stuff that we talked about? This is kind of the first one. We're like, okay, this is one of the reasons we studied all of those convergence and divergence things. So, okay, well, let's move on. Let's give you guys a chance to do some more with this, unless there are any questions. If any of you are thinking, this is neat and everything, but like, what's the big picture? You know, like, how can I connect all these concepts? If you ever feel that way, definitely let me know. I feel like you are doing okay with that. But if you're ever kind of like, whoa, wait a minute, I just all of a sudden got lost, please do say something. I can certainly understand how somebody could feel that way. Okay, so number 3, let's see if you guys can do some of your own original work here, right? So this says, find the 4th degree Taylor, no longer Maclaurin, find the 4th degree Taylor polynomial for f of x equals natural log of x, not centered at 0, but centered at c equals 1. So this is kind of like that second little video that we did. So I'll give you some space, time, room to experiment and try this. Compare answers. I'll be around to help if you need it.
Have to be third term, but isn't in the Taylor construction that like it goes x minus squared, x minus c cubed, so wouldn't it?
Well, so what I was saying, well, yes, but if your third derivative were 0, that's kind of what I was getting at. But yeah, you definitely want to proceed 1, 2, 3, 4, 5 up the polynomial. So yeah. Any other questions? Does anybody? I'm looking around. You guys look like you have reached some kind of a stopping point. Okay. Blake is writing. Yes. Are you done with this one? Pretty much done. I just don't want to rush anybody. There's no need for us to rush. How's everybody doing? Okay. Well, let's just conclude then. So then, did you guys get a third derivative of 2 times x to the negative 3? So this is where this one gets a little bit unique. Compared to the first 2 terms, f triple prime of 1 would just be a 2. Right? 2 times 1 to the negative 3. Okay, so then we'd have plus 2 times x minus 1 cubed over 3 factorial. And then the last one will be a 4th derivative. So I'm just going to write f parentheses 4 up there. That would equal negative 6 x to the negative 4th. Therefore, the 4th derivative of 1 would equal negative 6. So then our final term would be minus 6 x minus 1 to the 4th over 4 factorial. What do you guys think? Any questions? There's obviously some simplifying you could do here, right? The 2 would cancel with the 2 and the 3 factorial. The 6 would cancel with the 3 and the 2 and the 4 factorial. So you could definitely simplify some things. There's nothing wrong with that. There's also nothing that says that you have to do that either. So just be flexible on that. Is this series alternating or not? It is alternating. It looks, at least it looks at this point it is. You see plus, minus, plus, minus. I think based on looking at the way the derivative works, do you see how every other derivative will be positive, then negative, then positive, then negative? So I feel pretty confident this would be an alternating series for the rest of it, for the whole domain. Okay. Again, big picture question. Like, let's say you wanted this polynomial to be a good approximation for natural log of x. You figured out your error bound, and you thought that error bound is just way too big. What could you do to the polynomial to decrease the error bound? Yeah, just go with more terms. Add on we got 4 terms right there. You could add on a 5th, 6th, 7th, 10th, 20th. If you got a lot of spare time, 100th term or something. And or you could just program a computer and it would be much easier. Okay, still doing okay? All right, let's move on. Let's see if you guys can handle number 4. Can. So it wants, this would be a 3rd degree Taylor. Sometimes you'll see this notation. I'll just write this a little bit different just for sake of being different. Sometimes you'll see t sub 3 of x standing for a Taylor polynomial. I think p is probably the more common letter, but you might see this too if you're working on something that's a little bit different. Okay, so then your first term is going to be based on f of the centering point. So it'd be f of pi over 6. So what's sine of pi over 6? 1/2. All right, so we're off to a good start. So we're looking for third degree, so that's the 0th degree. So I'm going to move on to the first degree. So first degree is going to be based on f prime. So f prime of x is equal to cosine of x. So f prime of pi over 6 equals cosine of pi over 6. And that would be what? Root 3 over 2. Okay, so plus root 3 over 2 times x minus pi over 6, all to the first. So we're looking for third degree. That's obviously first degree. So we got a couple more terms to go. You guys doing okay with this? Okay, well, I'll let you just roll on for another few minutes, see if you can come up with the other two terms for this one. We'll check your answer in a second. Well, make sure we all agree. F double prime of x would equal negative sine of x. So f double prime of pi over 6 would equal negative sine of pi over 6. So do you guys get negative 1/2 for this coefficient? Okay, so negative 1/2. So it'd be minus 1/2 times x minus pi over 6 squared over 2 factorial. That's your second degree term. It's also your third term. Does that make sense? And then finally, to get that third degree term, I'm going to go f triple prime of x is equal to negative cosine of x. So then hopefully you're starting to see the pattern here. F triple prime of pi over 6 would be negative root 3 over 2. So then the last one would be minus root 3 over 2, x minus pi over 6 quantity cubed all over 3 factorial. And can you see why I only wanted to go third degree here? It's pretty tedious, right? I mean, there's a lot of effort that goes into such a short expression. There you go. How's this going? Are you getting this? I'm sensing that you are. Going okay? Okay. Did you notice that this one was not really an alternating series? This one went plus, plus, minus, minus, so it sort of feels like an alternating series, but technically not. And so if we were to try to use this to approximate sine, we would actually have to use a different error bound than the alternating series error bound, and we'll look at that, probably get to that tomorrow, I would guess. No, anyway. So we've got a few minutes left here, and I definitely want to do this. Got 5. This is going to work out this is going to work out so beautiful. So we're going to do number 5 for sure. It really is. It's going to work out really, really good. So number 5 says the first 3 terms of the Taylor series for this totally unknown function. So like g of x, we have no clue what that is, and I don't think we ever will. But I do know that the first 3 terms of the Taylor series are right here. So somebody has gone before you and they've figured this out, and they've left g of x, like as to what it actually is, they've left it to be a mystery. And frankly, we don't even really need to know what it is. Until you look at the last part here, the question says, what is the value of g double prime of 0? And so you think, okay, hold on. I would like to know what g is, so I could therefore find this g double prime of 0. The only thing they've given us is this Taylor series for g of x. And so I would like to give you guys a few minutes, maybe even like 4 or 5 minutes, something like that, to kind of let you try to figure this out. If you think about the Taylor construct, should help you. When you look at some characteristics here, notice some commonalities, similarities, differences. You might be able to just wrap this up in 5 minutes, maybe. I bet you if I gave you a half hour, I bet you'd come up with it for sure. There's no doubt in my mind, but 5 minutes might be pushing it, maybe not. We'll see. Try it. The first is this. When you look at this word right here, wouldn't it be fair to say that this is really a Maclaurin polynomial? How could you tell it's a Maclaurin polynomial?
G double prime of 0.
Yeah, well, so I think there's a couple of indicators. I mean, I'm asking you about 0, what's happening at 0. And then also, did you notice that all of these x's are just x's? None of them are like x minus 1 to the first, x minus 1 squared. Nothing like that. And so since they're essentially all x minus 0, then x minus 0 squared, then you can be pretty positive that this is centered at 0. So it's really a Maclaurin series, or you could say a Taylor series centered at 0. And the idea that you brought up is the same thing that Darian brought up, and it's this. This is so huge. The polynomial approximation for g of x is only perfectly accurate at the centering value. So if I were to give you some polynomial like this that's clearly centered at 0, and then say, what's g double prime of 2? I'm asking a really bad question because I've only given you information about what's happening at 0, and for me to ask, hey, tell me exactly what's happening at 2, it's a bad question. I need to make sure that what I'm asking you about goes along with where I centered the polynomial. You could maybe approximate g double prime of 2, sort of, kind of, but you certainly couldn't say this is what it is. So here's what I would do with this one. Once I recognize this is really a Maclaurin series or Maclaurin polynomial, I would write it out like this. Maybe I'd say p of x equals g of 0 plus g prime of 0 times x plus g double prime of 0. Hey, that's what I wanted, right? I wanted g double prime of 0. What I would then attempt to do is match up the correct term in the Maclaurin construction with the correct term in the polynomial. I would match then this with this, right? X squared with x squared. And I could then say that 3/5 has to be the exact same thing as g double prime of 0 over 2 factorial, or just 2. And then to find g double prime of 0, it's just a question of multiplying over. So you could just say g double prime of 0 is equal to, I saw this on a lot of your papers, 6/5. Yay. So really great start. Tomorrow we'll review this construction process a little bit, and then we'll get into the question of how do we bound the error if it's not an alternating series. That's how we'll probably finish tomorrow. So super proud of you guys. You're doing awesome.
Thank you.
Have a wonderful day.